So our first discussion in simple harmonic motion, or this whole periodic motion, is going to be about Hooke's law. So one of the big names in British science that people always think of is Sir Isaac Newton, which is absolutely correct. He was huge, and that's an understatement. There was another gentleman who lived in Newton's time, also very significant, and his name is Robert Hooke. If you've taken biology, you've probably heard of Robert Hooke. He did a lot of work around plant cells in the microscope. But Hooke was one of those multifaceted scientists, as were scientists of the day. He kind of had his finger in more than one pie. So biology likes to remember him for a lot of his work on plant cells and the microscope. Physics, we like to remember him for his work on elastic materials. So Hooke made an observation that we now know kind of falls under, we'll say, the domain of common sense. So Hooke recognized that if you applied more force or more stress on an object, the more strain that it's going to undergo. And by strain, we just mean deformation. So we can do that in different ways. We can squeeze something, we can pull it, we can twist it. So, we have an elastic band here. Nothing's happening to it right now. But, if I start to apply a force and pull it, we're starting to cause some deformation to it. And then, we can certainly squeeze it and twist it. We can do all these things. Now, Hooke noticed that for the most part, if you stop applying this force, the object's going to go back to its original shape. So, I have the elastic, I pull on it. If I stop pulling on it, it's going to go back to its regular shape. But there's kind of two exceptions. If you stretch or compress the object too much, so if you apply way too much force, like for example, if I take this elastic, I continually stretch it, eventually it's going to break, it's not going to go back to its original shape. Or if you have the case where the applied force has been applied for too long of a time, so for example, if I'm coming back to this elastic, I kind of grab it, if I hold it in this position for quite a long time, what's eventually going to happen is, the material inside of it's going to break down and it's not going to return back to its original shape. So in that case, what we've done is we've permanently deformed the objects. What we've done is we have stretched it to its elastic limit and beyond. What we want to do in this course is we're going to assume everything is kept below the elastic limit. So if we stretch it or compress it, it will go back to its original shape. We're also going to be dealing with ideal springs and everything else, like ideal elastics, ideal springs. Anything that stretches or compresses, we're going to say it's ideal in the sense that we're going to treat it as having no mass. So with all of Hooke's observations, of course we want to put that into mathematical into mathematics. So mathematically, what Hooke figured out is that the force is directly proportional to the displacement. So this is a linear relationship. So if it's linear, we know if we plotted f as a function of x, we're going to get a straight line. I probably should have my straight edge to do this. So let's try that again. We'll make this line a little bit more straight. So that's the kind of relationship we expect. And this is what we call Hooke's law. We're going to expand on that a little bit more. This is not the end of the story. So if we want to put it in words, we could say that the deformation of an object is proportional to the force causing that deformation. So it is a linear relationship. If you double the displacement, you will double the force. If you have the displacement, you will have the force. Now again, we have a proportionality, but we want to have that constant of proportionality that links both sides. And this comes from the fact that each elastic object is going to be unique. Some are going to be easy to stretch or compress, some are going to be difficult. So for example, I have these three elastics here. This one's really thin. Like I can stretch it out, I don't really have to apply a significant force. This one here, it's a little bit more difficult to stretch out, I have to apply a bit more force. And then this big one here, this is huge, so to stretch that out, I have to apply a much larger force. So all of these, because there's different forces I need to apply in order to stretch them out the same amount, there has to be some constant that relates to the amount it stretches or how stiff it is. And this constant is what we call the elastic constant. You're probably going to be more hearing it called the spring constant because we usually use it in the context of springs. So this is the letter K we use for that. So Hooke's law is going to be this F equals K times X. So F is going to be the applied force, K is going to be the elastic constant in newtons per meter, and X is going to be this displacement from equilibrium. And I'm going to touch on that in a second because that has a really important point that we have to watch for. So the K value, it's kind of a measure of the stiffness of the spring. A smaller K value, it's going to be a very loose spring or a loose elastic material, very easy to stretch. A very large K value, that is going to require more force to stretch it out. The big thing, and this is why it's underlined here, is this is the displacement from equilibrium. Elastic objects will have a resting position such that when you don't apply any force, there's going to be kind of a position that they have, or a length that they have, and this is what we call a natural length or an equilibrium length. Now, when we stretch it, we're not looking at the total distance of the material, we're looking at how far it's actually displaced from equilibrium. So for example, this spring here, this has this natural length here. Well, let me call this x0. Now, what we have here in this spring here, we have this total distance that could be measured, but what we'd actually be interested in for looking at Hooke's law is we're interested in the actual stretch from equilibrium. So this distance here is actually what's important. If I'm looking at this spring here, it's this distance here. So what we want is we want that distance from equilibrium. So like for example, if I have this elastic here and I want to look at determining the elastic constant of it. So right now I'm going to anchor it, I'm going to anchor it on this line here. So we're going to anchor it there. And without stretching it, here's kind of where it's at. So I could call this x0. Now I could certainly stretch this thing out. Maybe I got to change my position of my hands. So I stretch this out a little bit and I stretch it out to this point right here. Now, I would have to have a force meter to do this, to find the force, but let's say that is my distance I stretch it out to. So what I would be interested in for Hooke's law, in order to actually determine the spring constant, this is the distance here I would use. I want to find that distance from equilibrium. So that is something you have to watch for in Hooke's law. It's something that gets people all the time. So, be really careful with that one.